right, it's 3:30, so we'll go ahead and get started. Good afternoon, everyone, and welcome to today's EOL Seminar. I'm Sarah Woods, and on behalf of EOL, I'm pleased to introduce Dr. Bart Geerts. Dr. Geerts received his bachelor's in physical geography and master's in irrigation engineering from the University of Louvain in Belgium. He then went on to achieve his doctorate from the University of Washington in atmospheric science under the guidance of Peter V. Hobbs. Dr. Geerts conducts research in a cloud scale to mesoscale atmospheric processes through observations and modeling. Much of his research builds on experimental observations, primarily radar data collected aboard the University of Wyoming King Air. He participated in several multi-institution field campaigns, some in leadership positions. He has taught many graduate level and undergraduate level courses in atmospheric science, which has contributed to a broad understanding of the field. He has advised and graduated 28 master's and 12 doctoral students, while also co-authoring an undergraduate level book and over 150 papers in the peer-reviewed literature. He is the PI on a $15.8 million NSF Mid-Scale Research Infrastructure Award that is building the next generation King Air atmospheric research aircraft. In addition, he's received over $8 million as PI, $22 million as co-PI of external research funding over the last 25 years, mainly from NSF, NASA, NOAA, and the DOE. Dr. Geerts is a recipient of the 2012 National Institutes for Water Resources Program Impact Award. He's a fellow of the American Meteorological Society and has served as editor for one of the AMS journals. His service has also extended to several UCAR committees, several AMS committees, and to numerous federal proposal review panels. Dr. Geerts received the 2013 Samuel D. Hakes Outstanding Graduate Research and Teaching Award in the College of Engineering and Applied Sciences at the University of Wyoming, 2014 Faculty Senate Speaker Award, and the University of Washington 2018 Biennial Peter V. Hobbs Lecture Award. Please join me in welcoming Dr. Geerts for his seminar titled Shallow Convection in Marine Cold Air Outbreaks, Boundary Layer Processes, Precipitation, and Mesoscale Organization.
Thank you, Sarah. And thank you for the opportunity to give this seminar. And thank you all for being here. So it's an honor for me to give this seminar on a topic that I've been working on for about 5 years now. You're all familiar with the characteristic cloud structure of cold air outbreaks over open water. It's a boundary layer process. Precipitation formation is important, and then entrainment mixing in the boundary layer top. It's an interesting interaction between the underlying water surface and aerosol cloud precipitation processes. They're very common. Various places, especially downwind of boreal continents during cold air outbreaks or post-frontal flow conditions. You're all familiar with satellite imagery that displays such clouds, and they're basically large-scale subsidence in a post-frontal environment. But nevertheless, significant precipitation can fall from these relatively shallow convective clouds. Lake effect snow is well known, especially for lake effect situation where there's a long fetch along the lake. For instance, the eastern Great Lakes have very heavy lake effect snow sometimes under westerly southwesterly flow. And that's something we studied way back in the EOL's campaign, Ontario Winter Lake Effect Systems. So they can be hazardous. And that is one reason why we study them. Coastal heavy precipitation, erosion, also in the presence of polar lows over larger bodies of water, you can have hazardous navigation situations. But more importantly, maybe they are difficult to predict and capture in climate models. They fall in a gray zone, essentially a zone where much of the cloud and precipitation is a result of vertical motions that are sub-grid scale, that are finer scale than typical models resolve. You really have to go down to the LES resolution to capture these fine scale vertical motions. This convection is the least understood of a rapid air mass transformation. At the same time, the cloud regime that we study here is an excellent natural laboratory for the study of aerosol cloud precipitation interactions because you have a well-defined upstream boundary where no clouds typically exist at the coastal boundary or the Arctic ice edge. And you can examine evolution as a function of fetch from that edge. And then within the Arctic in particular, CAOs combined with warm air intrusions are an essential component of the changing climate. And as you know, the Arctic is warming 3 to 4 times as fast as the globe. So this exchange, meridional exchange of heat, is an important component in understanding Arctic warming. And then finally, from a global perspective, in a globally warming climate, there's concern about, or there's poor understanding of the cloud climate feedback. For instance, in a warming climate, it is feasible it's possible that a warmer cloud will have fewer ice particles and therefore maybe less precipitation generation, mixed phase precipitation development, and therefore a longer lifespan, and therefore higher albedo, and therefore more solar radiation reflected, which would be a negative feedback on warming. But other pathways are possible. It's really a poorly understood challenge, especially at high latitudes, both the Southern Ocean and the Northern Oceans. Postfrontal clouds tend to have a poorly understood cloud phase partitioning between ice and liquid. Measurements are not all that robust in cloud phase identification for these relatively shallow postfrontal clouds with cloud tops -5 to -20 Celsius. And climate models tend to underestimate the brightness, the albedo in the postfrontal clouds. They tend to dissipate those clouds more rapidly than observed. So there's a lot of interest in these cold air outbreaks, and various campaigns have been conducted. Here's a schematic of the typical cloud structure from Pithan et al. Under these strong surface sensible and also latent heat fluxes, you will see cloud streets developing in a sheared environment. Cloud streets align more or less with the wind shear. Helical roll circulations develop that basically aggregate the shallow convection into streets or bands. And then further downwind, it transitions to an open-cellular, sometimes a closed-cellular convective structure. Still fairly shallow clouds, 2 to 3 kilometers, occasionally 4 to 5 kilometers deep, with open-cellular clouds being the dominant cloud structure in most situations. And satellite imagery and satellite, spaceborne radar and LiDAR images have captured these. For instance, this is a CloudSat Calypso pass over a major cold air outbreak some years ago. You can see the increase in depth from the sea ice. The cloud depth increases in the Calypso backscatter power, and also the radar reflectivity indicates that there is precipitation there. This is W-band reflectivity from CloudSat. And then above that, you can see some water retrieved variables, effective radius and total water path. They're pretty uncertain, these retrievals, because of the extreme heterogeneity of the clouds at the footprint size that is typically smaller than the resolution of these spaceborne probes. So zooming in on one section, the temperature from ECMWF is shown on top. You can see some cloud tops that seem to have backscatter power, fairly high backscatter power, possibly indicating liquid. And below it, there is a fairly high reflectivity, 10 dBz or so, indicating snow. But then just to the right of it, you can see some backscatter without an underlying reflectivity signature, possibly indicating just a liquid cloud with virtually no detectable precipitation or radar return. We also know from the Sentinel synthetic aperture radar that these cold air outbreak clouds really modulate the surface winds. You can see variations in the wind structure. In the top panel there, cloud street region, there's a lot of fine-scale texture in the wind. And it's even stronger down at the lower panel there, the open-cellular regime, where you can see variations in wind speed from maybe 5 to 20 meters per second surface winds, estimated from the SAR imagery. At the scale that roughly matches the scale of the clouds themselves, as seen as the lower right image. So these clouds, these convective clouds, somehow alter the surface wind pattern. We'll come back to that. So this is a complex interaction. As called there is advected over open water. These strong surface heat fluxes produce a convective boundary layer that gradually entrains more and more free tropospheric air, basically isotropic layers that gets entrained into the convectively mixed layer. At least in the high latitude regions, these clouds are mixed phase, that is their tops are well below freezing and they tend to have ice. That produces precipitation rapidly, and in a campaign I'll mention in a moment, we see this immediately developing as clouds come off the ice edge. And then eventually, when the clouds become deep enough, the precipitation heavy enough, and at the same time, the surface heating remains high enough such that you have a relatively dry layer below cloud base, then you get cold pool development, and that then in turn seems to impact the surface heat fluxes, also affects the mesoscale organization, the popcorn structure that we see in the background. Precipitation is a result also of aerosol. This cloud regime is actually a good environment to test how cloud-active aerosol impacts precipitation generation under different temperature conditions. And of course, from a climate perspective, it's the change in albedo that matters during the time that at high latitudes the sun is out. And ice itself is important in the cloud life cycle, and fundamentally also it is a good environment to study primary and secondary ice production. All these processes are very phase dependent. Intensity matters too. The intensity of the surface winds, intensity of the surface heat fluxes, they're going to alter the structure that you see downwind. So what I want to talk about here is how vertical motions and convective circulations, mesoscale circulations, impact cloud and precipitation growth processes. It's very much an interactive process. And basically, it's a story about different type of flow patterns in the high latitude. I'll contrast first to CAO cloud regime against warm air intrusions, then brief expose about polar lows, some examples of the cloud streets at higher latitude, close to the ice edge, and then at greater fetch, we'll look at open and closed cellular clouds and the dynamics of open cell convection. Data that I will be using come from two campaigns. One is a fixed site or two fixed sites in northern Norway on the island of Andøya, on the outer islands of northern Norway there, where we had the Arm Mobile Facility number 1 deployed for 6 months, and late 19 and early 2020. We also well, first of all, we had quite a range of instruments, scanning, Ka and W-band radar wind profiler. The most widely used instrument was probably the Ka-band profiling radar, CASER, reflectivity, Doppler velocity, and spectral width. The aerosol observing system, including ice nucleating particles and other cloud-active aerosol. Let's see. We have a dysdrometer, two different microwave radiometers from different companies, micropulse LiDAR providing backscatter power and depolarization ratio, ceilometer provides cloud base height, ARI is basically an infrared spectrometer providing temperature and humidity profiles, as does the microwave radiometer, which also provides liquid water path, eddy correlation, radiation measurements, precipitation measurements. Quite an array of measurements. There were also some measurements on an island further north, about 500 kilometers north, at 75 degrees north, where Met Norway deployed various instruments from ARM. That collaboration between Met Norway and the ARM facility was really instrumental in making it happen. For instance, they had a C-band radar on top of a hill there right along the coast, and they also launched radio sonde balloons every 6 hours. Beautiful sight up in northern Norway right along the coast, at least in the summer. And then we had the CAESAR campaign this past year, just about a year ago. We had the NSF NCAR C-130 with various remote sensors, the Wyoming cloud radar looking up and down and slant back for cloud precip and vertical velocity, Marley, Raman LiDAR, temperature, humidity, and backscatter power, KPR, Ka-band profiling radar for more focused on precipitation because it attenuates less, the GVR from the University of Miami for water vapor and liquid water path, and then a number of in situ sensors, also cloud imaging, sizing probes, aerosol probes, and of course the drop sondes, very important. Beautiful place, Kiruna in Sweden, quite a team, and we didn't fly as much as we had hoped, but we collected a wonderful data set. And so I'll start with some contrast of CAOs versus WAIs, warm air intrusions. So we define CAOs, colder outbreaks, as having basically thermal instability over the water. That is, the theta of the sea surface temperature is above the theta at 850 millibars. It's a widely used index of thermal instability over open water. And then warm air intrusions we define as a situation where the atmosphere or the lower atmosphere is basically decoupled from the underlying surface. Theta E increases with height. And in both cases, we require at least 10 knots wind speed. And it turns out that this occurs about 19% of the time, both of them. During the 6-month period that we deployed all the instruments in the 2019 to May 2020 period. In red, the warm air intrusions, and in blue, the cold air outbreaks. We're going to look primarily at the 13 March event. And very beautiful satellite imagery there with radar imagery along the Scandinavian coast for a CAO on the left and a warm air intrusion on the right. And for a warm air intrusion, I'll go from Combo to CAESAR and show an example that we intercepted by chance. We did fly with the C-130 up north to some CAO cloud regime on our FO2, the 29th of February. But to get there, we had to go through a frontal rain band, which itself was very interesting cloud structure. So the C-130 flies out and back. There was this lawnmower pattern or some sort of zigzag pattern that we did up north in the CAO regime, but I'm looking at the precipitation band below, and it's clearly a frontal structure. You can see some sloping isotropes. That theta V comes from a Rome Arctic operational model, high resolution model. And there were 2 drop sondes, and you can see the temperature difference plotted on a SKUT there on the far right side. It's about 8 Kelvin temperature difference over a distance of about 500 kilometers. So clearly baroclinic, deep frontal. And looking at the hydrometeor vertical velocity from the WCR, looking up and down, the white line there is the flight level, the radar blind zone essentially. And what's plotted here is the best estimate vertical motion of the hydrometeor. So that includes a fall speed, VT. And if we assume here in the third panel that we can ignore the average air vertical velocity along the entire section and remove that residual, which we assume is the height-dependent fall speed, then we have the air vertical motion locally displayed. So the hydrometeor vertical velocity is primarily blue downward motion. Fall speed of particles is what comes out, except at the very top. And then the air vertical motion is plotted between -2 and +2 meter per second, so a more narrow range. And you can see there's really not much vertical motion. It's a very stratiform environment. Very low spectral width, that is basically the variance in the Doppler velocities. And if you look in the upper right there, you can see some interesting cloud top generating cells for those of you that are studying this or have studied this. I know some of you have. And these are very large features, actually, on the order of 10 kilometers wide, 2 kilometers deep. I don't think they're typically that size from what I've seen in the literature. So these are exceptionally large features. They are found just below a cap, a well-defined stable layer. The theta V lines are shown up on top. It's also very dry. These blue contours indicate humidity, relative humidity. So, but within this 2 kilometer deep layer, it's actually relatively well mixed. Theta is fairly uniform. It's nice to overlay the model thermodynamic information with the radar data, so you come to understand this, the dynamical processes a bit better. It's not quite clear whether this is upright convection driven by positive buoyancy. If you look at the vertical velocity pattern here, red is up and blue is down. There's a lot of variation in vertical motion, plus or minus 2.5 meters per second. But from just looking at this, it's not clear whether this is positively buoyantly driven or negative buoyantly driven by radiative cooling on top and some negative buoyancy, as Jason's work has shown. It's modeling work. Anyway, there's some relatively high spectral width and clearly convective motions above the very stratiform clouds. Beautiful sheared virga here. And you come down into the layer where you are in the dendritic growth zone around -14 Celsius. Clearly a situation where the generating cells generate ice and then feed the dendritic growth zone and produce relatively heavy precipitation near the surface. All right, now let's go back to what we were talking about, the cold air outbreaks. They can be deep. This is one of the deepest events in that 6-month period, up to 5 kilometers. For the Arctic, that's almost like deep convection. We talk about shallow convection, but this is close to the depth of the tropopause. If you look at the QT, you go up to 500 millibars, and you basically are at your tropopause. So very low tropopause. So this is almost like deep convection. But that's exceptional. Usually they're not as deep, and you see clearly this is base surface driven. There's strong vertical velocity variations. And you see updrafts, also regions with strong spectral width indicating, turbulent motions as typical for convection. These are all measurements from the site at the coast there called Andenes. Before Caesar in Comble, and there's some clouds that have high liquid water content, like this one here, high spectral width, strong updraft, but then others like this one, more bottom heavy, very low spectral width, no liquid water, probably an older cloud, so there's something about the life cycle of clouds that you come to detect. And if you composite all these periods of CAO and WI conditions, you come to see typical patterns in the vertical profile. It's not just that colder outbreaks are colder, they're also better mixed. You see fairly uniform theta and theta E in the CAO compared to slightly stable or more stable conditions in warm air intrusions. And that leads to a fundamentally different kind of cloud structure, different dynamics. Vertical motions are convectively driven as opposed to baroclinically driven. Cold air outbreaks are the result of strong surface sensible heat fluxes. That's also a region where the latent heat fluxes are pretty large, and that then leads to precipitation production. So Adriana Bailey's work has shown that in Caesar, much of the water vapor in this boundary layer comes from fairly local sources, the local ocean. Whereas in warm air intrusions, Water vapor typically transported from far away, long-range transport. Very high values of IVT, integrated vapor transport, basically coming close to values that you see in atmospheric rivers. So very different environment. But both of them can produce significant precipitation on average. This is the total precipitation for the two regimes, both occurring about 19% of the time over a 6-month period. And it's actually remarkable that these shallow CAO clouds produce fairly significant precipitation, mostly coastal precipitation, but also over the open water. The vertical structure in the CAOs is quite different from warm air intrusion. So CAOs tend to be more shallow clouds, occasionally deeper. They tend to have slightly more variation in Doppler velocity. This is from the CASR vertically pointing radar. It's not like there's a lot of graupel or hail there. You don't see extreme fallouts. Doppler velocities exceeding 2.5 meters per second almost never happen. So at most it's graupel, lightly rimed graupel. And then spectral width is also broader, indicating turbulent motions as well as variations in the fall speed of the particles. Ignore the lowest part of the warm air intrusions. These high values are the result of snow transitioning into rain, producing a much higher fall speed and more spectral width. All right, now I'd like to have a brief excursion talking about polar lows. We observed one in Caesar, and in Combel we actually had 3 making landfall at our main site. They occur fairly commonly actually in the Norwegian Sea, but also in other places. For instance, in Gulf of Alaska, they occur occasionally. They're mesoscale lows. They have a convective component and typically also a baroclinic component. Here's the one that we observed in Caesar. We tried several times to sample one, and then finally we managed to get the C-130 into this polar low. This is Svalbard up here, and the Scandinavian coast is just off the map. So you can see this is associated with a cold air outbreak. And this is the flight pattern we did, and the pilots were probably wondering what were we doing flying back and forth from these different angles across the polar low, trying to come close to the eye in all these transects. My master student, Evan Newman, has been studying this case. This is a situation under northerly flow at all levels, really, fairly shallow tropopause. These are back trajectories, and you can see how the color changes, potential temperature changes, and air mass modification. Manifestation, basically. Top panels are sensible heat flux, the bottom panels latent heat flux at 2 different times together with sea level pressure, and sections of the flight track in brown. And you can see there's a fairly high sensible and latent heat flux, especially sensible along the ice edge. There's ice between Bear Island and the bottom of Svalbard there. So there's very low sensible heat flux there, but then as soon as the air comes off the ice, you see high values going over 200 watts per square meter. And sensible heat fluxes tend to be higher further south. So this was not a strong polar low, but nevertheless one, intensified somewhat as it traveled north to south. It was supported somewhat by an upper level PV anomaly at 500 millibars. You see a maximum in vorticity and on the right side in the red, and taking a cross section from basically north to south, left to right, up to 300 millibars. The potential vorticity is color filled. You can see an upper level positive PV anomaly, upwind of the low level positive PV anomaly, which is quite small in this transect. Red values have PV values that essentially are stratospheric values, more than 2 PV units. And there's some baroclinicity there too. This is 850 millibar temperature. You can see it's colder to the Barents Sea on the east side, warmer in the Norwegian Sea on the left side. And at the same time, there is surface driven convection, as you can see, cloud streets transitioning to open-cellular clouds on the west side of the polar low. On the far east side, there's also open-cellular convection, But then closer into the polar low, there seems to be some fuzzy cloud tops, more stratiform cloud tops. And then there's a very shallow, young CAO cloud regime that comes off the east and sort of collides with the northerly flow from the Fram Strait to the north. So there is some convergence zone in here as well. So different air masses collide in this case. And the C-130 did 5 transects. We'll just look at the last transect. Here it is again with the sea level pressure from around Arctic and the satellite imagery in the background. And this is the transect basically from west-northwest to the east on the right side. And you can see the more convective cloud regime on the left side, basically mature CAO convection on the west side. And then on the far east side, you can see some stratiform mid-level clouds. Theta V contours are overlaid. You can see that it's fairly well mixed up to near cloud top on the left in the convective clouds, but the stratiform clouds, there seem to be many isotropes, maybe 5 of them, before you go into that stratiform cloud top. So that's decoupled cloud aloft. In the center there, the isotropes are a little bit lower. The low pressure is somewhere there, with big letter L. There seems to be some subsidence. Convection is suppressed. We have 1 drops on there. The flight track is a porpoising one. We go up and down through the cloud. The color variation along the flight track shows virtual potential temperature. So it's a combination of our own Arctic data with observations, and the model actually did reasonably well. There may have been some offset spatially, but it captured the polar low reasonably well. Now if we plot some other variables, vertical velocity in the second panel, spectral width in the third one, and then the LiDAR backscatter power above and below flight level in the last panel, together with some other Arctic variables contoured, we gather a more complete picture of this cloud. You can see that the cloud on the left, the convection, has high spectral width, with theta E decreasing with height in the first kilometer or so, indicating that it's coupled with the underlying surface, and the cloud tops are close to the theta E that you encounter at sea level. It's weaker, the potential instability is weaker on the right side, and there's 2 theta E contours in the higher cloud layer, which clearly is decoupled. So that's more like a baroclinic structure. The theta V lines are somewhat sloping. So it's a combination of convection and some baroclinicity that explains these clouds. And they have different aerosol characteristics too that I will now go into. So that's it for polar lows. Now we go back to the CAO cloud regimes. We'll start with cloud streets just briefly, and then open cells versus closed cells. So Tim Giuliano did some simulations of a CAO in Combel, the 13th of March event, over the entire 1,200 kilometer length of the Norwegian Sea, from the ice edge down to the Norwegian coast, at a resolution of 150 meters, I believe. And this shows just one transect, the one in bold there on the right side. The bold red line indicates where this is. This is in the short fetch cloud street regime. You can see very shallow clouds. And the values that you see here actually model derived. The CR Sim radar simulator is used to convert model output into radar variables. So K-event reflectivity, as would be observed by such a radar, is shown on top. Doppler velocity, spectral width, then liquid water path, then surface temperature, and wind from west on the left side to east on the right side. So further south, you can see that the cells become open-cellular, and this is what it looks like within the LES domain that Tim simulated. And you can see clouds about 3 kilometers deep in this case. Open-cellular structure. Clearly, there's some subsidence between the clouds to make it open-cellular. And large variations in vertical velocities exceeding that range of velocities shown there, -3 to +1, high values of spectral width, and pockets of high liquid water path. So let's look at some cloud streets. We didn't really observe very good ones in owls because we did not fly across the cloud street structure. I was hoping that we'd get more of those flight patterns across the cloud streets. We did one in RF07, I think, for a short section, but we mostly flew along. Anyway, this goes back to an earlier campaign, the owls campaign I mentioned earlier. Looking for this helical roll circulation, it's not all that obvious. This is WCR dual Doppler, and I'm trying to find some close or some circulation structures, rising motion in the red colors and sinking motion in the blue. Quite a broad vertical velocity range. Plus minus 4 meters per second. So there may be some helical roll circulations, but it's not as shown in the textbook. There's also some variations in the along wind speed as a result of momentum transfer up and down. We documented that in an earlier campaign over Lake Michigan. I don't think I'll go into depth here, but you need the horizontal plane dual Doppler to observe that. So very little about cloud streets. I want to dig more into the open-cellular cloud regime. But before I go there, I want to contrast open versus closed cells. So open cells are the most common. About, let's see, 80% of the time during CAOs, we find open-cellular clouds, 20% closed cell. This is an example of the more intense open-cellular clouds. This is an example of closed cell clouds. Vertical velocities are smaller. Cloud depth is generally somewhat lower. But basically, there is not enough vertical motion to have both strong updrafts and then sufficiently strong downdraft to clear the cloud. And you have a continuous cloud deck. Spectral width tends to be lower as well. The ice phase is probably present here, given these relatively high reflectivities. And in this case, the cloud top is minus 15. There may have been situations in Commel where we had liquid-only clouds, more shallow clouds than these. So based on the, open cellular is 72% rather than 80%. Anyway, dominates. So open cellular clouds basically have more thermal instability. The M values tend to be higher. That's the blue histogram versus the red one, closed cells. They tend to be colder. Open cellular clouds also tend to have stronger surface winds. And in terms of cloud properties, they tend to have pockets of higher liquid water, although closed cells tend to have low liquid water pad, more prevalent. Open cellular clouds tend to be deeper, and they tend to have heavier precipitation rates. And since they're deeper, they also have a lower cloud top temperature. In terms of the vertical structure in CFATs, contoured or colored frequencies by altitude displays, reflectivity, Doppler velocity, and spectral width, again, the three radar moments, with the 10th and the 90th percentile shown by dashed and dotted lines, and the solid line is a 50th percentile. You can see open cellular clouds tend to be deeper, tend to have higher reflectivities on average. In fact, I'll overlay the closed cell mean values on top of the open cells. So that's from the closed cells, just superimposed here so you can see that contrast. And open cells tend to be just more intense, therefore also heavier surface precipitation. They tend to have higher variability. This is the variability from the closed cells. It's smaller than the Doppler velocity variability for the open cells. And spectral width tends to be higher with the open cells. So open cells probably are coupled to the surface, whereas closed cells may be decoupled from the surface. In order to examine that, let's look at some model output. This is again from Tim Giuliano. And this shows 12 hours of simulations of at a 30-meter resolution just off the Norwegian coast out here, about 70 degrees north. Norwegian Sea is out here. And the velocities are 10-meter winds. The purple stars indicate where snowfall occurs. And then you can see the winds are departures from the mean. And the temperature normally is color-filled. So you see warm pockets and cold pockets. In general, it warms towards the south. But then there's these pockets on the order of 10, 20 kilometers in diameter, basically cold pools. And cold pools tend to be divergent, and then they can collide. Also, that enhanced flow leads to stronger surface latent and sensible heat fluxes. Along the boundaries, that extra heat and moisture leads to buoyant updrafts, and that leads to more liquid water. And that then feeds the precipitation growth in mixed phase clouds that we see out here. That leads to enhanced surface precipitation, which then may evaporate below cloud base. And then in the deeper open-cellular clouds, you also have entrainment of free tropospheric air down to the surface, and we saw that in Caesar actually, feeding the cold pool development. So there is this this interaction, a feedback loop, if you like, to maintain this convection. Intricate part of that is the life cycle of convection that is within it. Initiation of convection under or above convergent boundaries, and then the decay of convection leading to cold pools. And that is actually shown in a still picture, one of these images. So the blue contours here are areas where heavy precipitation occurs. The darker colors is heavier precipitation. And the yellowish areas indicate areas where you see high liquid water path, vertically integrated liquid. There's various shells. They're not quite coincident. And here's an area with a lot of, or several developing cells. You can see the orange patches. And then just to the east of it, there is a patch that seems to be decaying because it has snowfall, blue contours, but it has no liquid water path. And if you then look at the coincident divergence, you can see convergence along the area with developing cells, high liquid water path, and divergence in the area of where the cold pool is expected under the precipitation. And in fact, you can see there's a cold pool in that same area, the old cell, and a warm anomaly in the area of developing cells. So the model, the LES model, captures this very well, provides the dynamically consistent context to understand the life cycle of this convection. Then if you look at the cross-section along the black line there, this is what it looks like. Dynamics on the left and microphysics on the right. You can see a convective updraft, then the turbulence associated with this convection. Strong vertical motions up to 5 meters per second. In small patches, it seems to be almost fractal. You see finer scale structures within. And in the microphysics, you see liquid water in the top panel there, in the areas of strong ascent. And then like a fountain spreading left and right is the ice near the cloud top. And then emerging from that ice is the snow, reaching the surface on the left side primarily. And that then produces somewhat of a cold pool, which leads to this convergent flow on the right side of it. So LES model captures these dynamics very nicely. These cells, as shown in the animations, tend to have a life cycle of about an hour. Cold pools, they dissipate also within about an hour. So what happens when cold pools occur, you get enhanced surface heat fluxes and rapid air mass modification. So that leads to their destruction. So there is a continuous recycling of moisture and heat. The convective life cycle is evident also at the Andenes side, looking at this time series, about 6 hours long here, of convection moving over the site. And I'll pick two cells. Here's one with fairly broad, pretty high reflectivities going up to maybe overshooting tops with strong vertical velocities, updrafts and downdrafts, high spectral wind indicating convective turbulence and possibly Graupel presence. High liquid water path and also ice water path, and a developing cold pool. Maybe the temperature is shown with the red line down below. under this onshore northwesterly flow at the coastal side. Then if you pick a different cell, the one to the right, you can see a bottom-heavy reflectivity profile. And the highest reflectivities are not near cloud top, but near the bottom. And vertical velocities are weaker with mostly downdrafts at low levels. And low spectral width, no liquid water, and somewhat of a cold pool here on the right side of it at least. Indicating probably a mature cell on the right, whereas the one on the left may be a developing cell. So in order to objectively separate between these types of cells and to really extract the life cycle of the convection, we did this analysis. This is work by Christian Lackner, who's now at Brookhaven National Lab. He identified cells objectively using a watershed technique where basically the minima, or rather the maxima in reflectivity, are identified, and then you move away from it until you encounter another cell. And then the cell needs to be a sufficient size, and you end up basically with these various segments that you defined in as cells. And then rather than analyzing the spatial structure of those cells, what we did is we analyzed their CFATs. So there's reflectivity, Doppler velocity, and spectral width. They all have their frequency by altitude displays. And an AI technique called cell organizing map was used to basically characterize these CFATs for all the cells, some 780 cells in total, in order to obtain some information about characteristic vertical structure of the three radar moments. Christian Lackner came up with 9 different nodes in the self-organizing map technique. And we'll just look at these 3 on the left. These are the more intense ones. They're all open-cellular clouds in red. The closed cell structures are more on the right. So just looking at these 3 on the left, they have relatively high reflectivity profiles. The averages that you see here in solid red lines are reproduced over there. And so there is 1, that's the top one here, upper left, upper right, and then 3-1 is the lower left here. And so they are more intense, all 3 of them. The middle one is the most intense ones in terms of reflectivity. But then if you compare them, the top one is more top-heavy and more heterogeneous. It becomes more homogeneous towards the bottom and more bottom-heavy also. The vertical motions, the Doppler velocity, also is wider initially and becomes more narrow towards node number 3. So there's some transition from high variability to weaker variability. And the same in terms of spectral width, which is a measure of turbulence, as I mentioned. Lower spectral width values in this bottom node, whereas the top node here has a large spectral width. So we interpret the top one as being developing intense, and bottom one as the decaying intense one, the mature intense one being in the middle. So based on the 780 some cells, we can find characteristic convective patterns that reflect the life cycle of deep convection. And they have different widths, and that is shown here with the mean and the 1 standard deviation. Not surprisingly, the decaying one has more of an envelope on top, slightly broader. In terms of temperature, let's see, the coldest ones are the mature intense ones. These are cloud top temperatures, whereas the developing ones and the weakening ones are somewhat warmer cloud tops. In terms of ice water path, it increases from the young to the old clouds somewhat. Well, the mature ones have the most ice, but in terms of liquid water path, you can see clearly a decay. These are violent plots showing the full distribution with the mean, I think, and this 25, 75%, and 10 and 90th percentile with the full distribution shown in the violent. In terms of the type of precipitation using an algorithm developed by the Mao Zhang in the DOE ARM group. Developing ones have more mixed phase clouds, and that implies that they have some liquid in them, whereas the decaying ones have, and also the mature ones have more snow in combo. And then finally, in terms of the precipitation rate, you can see heaviest precipitation rate in the decaying ones and weak in the developing ones. Temperature anomaly, slightly warm positive anomaly for the developing one, and a negative or cold pool anomaly for the weakening ones. So pretty much as expected. So the other 6 nodes were classified as well. These include closed cell structures and includes dissipating anvils. So in summary, this was a sort of a whirlwind tour through CAO observations. We find that CAO shallow convection can be deep, can occupy much or the entire of the Arctic troposphere. But that's rare. It requires a fetch of at least 1,000 kilometers and very strong surface-sensible heat fluxes. Typically, they are moderately deep. That's 2 to 3 kilometer deep, maybe. So maybe half to 1/3 of the Arctic troposphere depth. They tend to have intense precipitation, stronger updrafts, high liquid water path, but then also cells with very little liquid water path given the life cycle. Much of the water vapor comes from local sources, the underlying ocean, whereas WAI, moisture transport, is long range. Polar lows, actually I did not discuss any of the combo cases, but they all have a region of surface-based convection and then another region that's more baroclinic with stratiform precipitation. Surface heat fluxes are important. I did not show that diabatic PV generation is important. This is work that my student Evan Newman is doing with Jim Doyle at the Naval Research Lab. There's some upper level support in this case also. And also in the case that we're looking at in Caesar, there's actually a frictional source of potential vorticity. The island of Spitsbergen to the north is somewhat mountainous and produces these vortices spinning off the island. Open versus closed cells. Closed cell structure is less common, occurs under weaker thermal instability, weaker winds or lower surface heat fluxes. They tend to be shallower, less turbulent, weaker vertical drafts, lighter precipitation rate. Warm rain processes may dominate. They generally have some liquid water. Open cells are ice dominated, at least in this environment far north. And then open-cellular convection coupled with the underlying ocean exhibits a life cycle. That's evident from observations and is corroborated by LES simulations. Developing cells have the stronger updrafts, high spectral width, pockets of high liquid water path, minimal precipitation. Upon maturation, updrafts tend to decrease in strength. Cold pools develop as such. Open-cellular mesoscale organization is the result of convective life cycle dynamics. So convection really explains why you have that open-cellular structure, which is maybe not surprising, but it's really nicely illustrated by the combination of observations in the field campaigns and the simulations, the LES simulations. And I'll leave it with that. So open to any questions you may have. Thank you.
Thanks, Bart, for that broad overview, CAOs. Quick reminder for those of you online, you can enter your questions in Slido, which can be found on a tab right above the video screen. Do we have any in-room questions?
Very nice talk, a lot to digest, but from the very basic fluid mechanics point of view, if you look at those pictures, there are, many of them you showed, is clearly streets, and then it changes to either closed or open cells. Do we understand mechanics of that? What is involved? Clearly streets means shear. you have to have typically vertical shear to have those streets. That's kind of long known. Is that any underlying mechanism that kind of makes those streets break into open or closed cells? I would imagine there is, but you haven't touched on that. So that's something
Yeah.
that I would be curious. And of course, idealized modeling can help a little bit on that. And probably in some of those simulations, this transition happens, but it was not something that you kind of discuss.
Yeah, the cloud streets, they are so ubiquitous under sufficiently strong wind conditions when a convective bound layer, heated from below, develops, right? Shear must be a driving factor. Many studies have shown this, even early studies. Yeah, yeah. But eventually what we find is that the dynamics of convection take over. There's so much vertical exchange over the depth of the boundary layer that the shear becomes relatively small, and convective dynamics, the life cycle dynamics that we showed, really take over to produce the mesoscale structure that we see from satellite. Under sufficient surface heating, where the clouds are convective coupled with the underlying surface, to produce sufficient precipitation. The heating from below also allows for a boundary layer that is dry. Well, there's cloud base height is several hundred to 1,000 meters high. Therefore, you have low-level evaporation. Even though it's cold, a very cold environment, that evaporative cooling is sufficient to drive the cold pools. We see that in the model output. We see that in the temperature variations measured at Andenes, and also the C-130 did some flux lays at low levels and showed these
Kind of
temperature
follow-up
variations.
might be that you're basically arguing for the role of precipitation in the transition from rolls to kind of cellular structures, and I would think that this is correct. Yeah.
Yeah, I agree.
Great. Other questions?
Thanks, Bart. A very interesting talk. Of course, you caught my attention with the generating cells, and those are particularly wide. I find that interesting, and I was wondering if you had any thoughts on why they were that wide, or what role vertical wind shear at that altitude may have played in their organization.
Yeah, so that case of cloud streets that I showed, because you're here and Lulin is here, I think, well, for one, there was very little wind shear at that level, almost there. And it was also relatively well mixed, fairly strong shear at, here we are. Yeah, the wind profile is not shown here, but you can see the stability, right? And you can see that it's very relatively well mixed here over a 2-kilometer deep layer, where, well, the vertical structure of the convection also shows that there's fairly little wind shear. So I know you've looked at, in idealized simulations, the effect of shear on cloud top generating cells. I don't know, maybe the lack of shear in this environment and close to dry adiabatic or moist adiabatic lapse rate is conducive to larger generating cells.
Potentially, yeah, because I mean, granted, I'm relying on 10 years memory from that work, but I think what we had seen was that there were closed cell convection that was favored at cloud top in weak vertical wind shear, but also looking right at the top of that layer, you have much smaller updrafts and downdrafts there, which if right at the tropopause there you have sufficient shear, you could also be getting some KH billows right at the top. That would make sense of seeing the very small structures with the broader structures below them. So it could almost be a transition from weak shear below to technically, for the right stability profile, any amount of shear would be favorable for KH.
We can look at that some more. We can zoom in more. This is 65 kilometers. There is a lot of fine scale structure within the tops of these main structures, right? It's almost like a fractal structure. And maybe these are KH billows, yeah. We don't have dual Doppler, we only have that below flight level, but at least we have the vertical motions. Yeah.
Very interesting. Thank you.
Any other pressing questions in the room?
Hi, Bart. I have a question about one of the radar profile that you show. I guess it's one of the closed cell. It's showing the Doppler velocities. There is a constant. Maybe the next you passed it. Yeah, the previous one. Yeah, there is a constant updraft layer near the cloud top.
Yeah.
So what's the mechanism of that? Is that true vertical velocity or some bias?
It's a display. We choose to center it at -1, the color display. See that? Which is a typical fall speed of unrimed snow, as a way to see where the air rises or sinks as a first order indication. This is hydrometeor vertical velocity. It's a very well calibrated, very precisely mounted Ka band profiling radar. So these are hydrometeor vertical motions. And if we centered it at 0, this would be closer to 0. Very low velocities, because the tiny particles up there have almost no fall speed, right? Maybe 0.2, 0.3 meters per second initially. And then they start falling more rapidly. So why this rapid transition from there to there, I do not know. But the color scale is the choice of color scale really gives that impression that it's apparently rising at the top. That's not quite the case. It's just falling more slowly.
Can I comment on that too? Because that's because the color scale, the shift, give you that illusion, whatever you can say it. But the spectral width actually indicates something, because that top layer has a relatively strong spectral width to indicate turbulence and actually more active dynamics. So that's still slightly relevant to the cloud top dynamics.
Maybe small cloud top generating cells.
But it's almost like kind of two different layers, am I right? Because if you look at the top picture, it's kind of you clearly see the transition from kind of top, which is kind of green and blue, versus kind of reddish with those kind of high values when you get a lot of precipitation, am I right? So it's almost like maybe kind of two-layer structure, different dynamics in each, more convective, and I don't know, it just, the middle panel definitely shows that there is kind of small scales and reddish colors versus kind of bigger structures.
Yeah, I imagine that cloud top cooling, especially in the polar night, is an important factor in controlling the cloud top structure. There may be some cloud top ascent under weak stability, at least, because of convective motions, or at least, the cloud top generating cell structure seems to be present here, and it may well initiate ice at these temperatures. They're not all that cold, -15 or so, maybe -14, -13 Celsius or so.
What hours that fly, do you know that?
This is not a flight. This is a fixed location, 6-hour period at the star on the map. So it's not an aircraft flight.
What night, day, spring, so I can
Yeah, well, this is into the evening. Sunset must be about, this is April. I don't know exactly. Low sun for sure, and nighttime towards the right.
Thanks, Bart. We are past our hour, so out of respect for everyone's time, we will continue conversations offline. Let's thank Bart one more time.